As we work our way through Chapter 2, we come up on another linear function. This whole chapter deals with writing linear equations, graphing linear equations and functions. And today is another example of that, but this is a particular type of linear equation, and it's called direct variation. And so my goal for this lesson is for you to be able to recognize direct variation in equation form. When we're just giving a set of ordered pairs, can we tell whether or not those ordered pairs represent a direct variation line? If you're just given one ordered pair, can you write the equation of the direct variation that's represented? So there's a lot of different ways to recognize direct variation, and then we're also going to be writing direct variation equations. So let's get started. I worked through this with the class just as a way to get them thinking about how direct variation could be applied to a real life situation. And we have the upper school cafeteria who sells lunches each day for $5 for the lunches that our cafeteria actually makes. We're not talking about the ones that are catered in or we're buying from vendors. So we could very easily come up with a function that represents the amount of money collected, and hopefully you can see that that really depends. The amount of money that we collect is going to depend on how many students eat lunch. So right away, our independent variable, hopefully you see, will be the number of students who eat or buy a lunch. I'll just say number of students. And therefore, based on that number, we will be able to determine y, which is the dollar amount that's collected. So here's an example of direct variation. The dollar amount collected will be found by taking that $5 constant, $5 for everybody, times the number of people who buy a lunch. And that's pretty simple. If 200 people buy a lunch, then you're going to do 5 times 200, and that gives you the amount of money that's collected for that day for the people who bought a lunch. So this equation represents direct variation. I guess it's easy to recognize by what it does not show. And we talked about this in class a little bit. We're used to seeing slope-intercept form. Well, if you notice the comparison here, something that's always true about direct variation equations is their y-intercept, or b, will always be 0. It's like this invisible plus 0, 5x plus 0, of course, is just 5x. So if it truly is a direct variation equation, then the y-intercept is going to just be 0. Okay? And there'll be a number not 0 here serving as a coefficient. We think of this as slope, but it's also known as the constant of variation, and we're going to talk about that on the next slide. So this gets us into some practical homework help. You're going to be asked to recognize equations that represent direct variation. And once again, here's direct variation in general. Y equals some constant. We call this the constant of variation, known as k, the variable k, times an input number. Of course, we're used to seeing that as x. And the only stipulation we have on this is k can be any number, real number, except 0. Because if it is, this probably makes sense. If k is 0, then you just have the line y equals 0. And that's just another way of saying the x-axis. So that doesn't represent an input and then the output increasing or decreasing by a constant. So K can't be 0. It can be any other real number. And remember, the y-intercept for direct variation will always be 0. All right, so let's just take a look at some examples here. Do these equations represent direct variation? Well, letter A obviously does. It's very much like this. It's solve for y. The y-intercept is 0. It's K is not 0. So it meets all the criteria. So we're going to say yes. And then we're going to go another step and identify what this constant of variation is. And we would say that it's 3. Pretty simple. Letter B, very much like it. It's also direct variation. And in this case, we'll identify the constant of variation as -4. Letter C, however, has a y-intercept that's not 0. It's actually -4. So when our equation represents a number not 0, but for K, and a y-intercept that's not 0, we're going to say that it's not direct variation. And if it's not direct variation, then we don't have to worry about finding the constant of variation. Letter D, to be sure, I'm going to make it solve for y, just like this is solve for y. I'm going to solve for y first, and when I do, I get this equation. So maybe on the outset you said, well, it doesn't look like this equation, so it must not be direct variation. Well, you don't really want to make that conclusion until you've solved for y. And in solving for y, you hopefully can see that, yes, it is direct variation. And the constant of variation, of course, in this case is 3/4. Letter E, if we solve for y, we get 3x minus 2. Well, this is not direct variation because the y-intercept is -2, and it's supposed to be 0 for direct variation. Okay, so we took a look at this graph. This is the graph of a direct variation function. I noticed that it does go through the origin, 0, 0, which is always true of direct variation graphs. Remember, the y-intercept is 0. But notice what happens. Every time I do an input, the output is that number times 3. 1, output 3. 2, output 6. 3, output 9. See the pattern? 4, output 12. Every time I do an input, my output is that input times 3. So, even though I'm not told what the equation is, it's pretty easy to come up with it, because that number that I'm multiplying x by each time to get y is the constant of variation. So in this particular case, my equation would be y equals 3, the number that I'm multiplying by each time, x. And here's another way of finding k. We could just do some simple division. Y over x, 3 over 1 is 3, 6 over 2 is 3, 9 divided by 3 is 3, 12 divided by 4 is 3. Really, and the reason I did this is because if you think about it, k is just another way of saying what we're used to seeing, and that is the slope. Okay, so just take these 2 points, for example, and if you apply your slope formula that we learned, m equals y2 minus y1 over x2 minus x1, you get m is 3. And that's really the same way that we're looking at the constant of variation. It's just that since it's direct variation, it's given a little different name, but it really is another way of saying the slope of the line. All right. And you're going to be doing 2 through 8 even, but in this set of problems, the book wants to know if you're given a set of ordered pairs, can you recognize whether or not the set of ordered pairs is direct variation, or does it represent direct variation? Well, let's go back to what we learned about that constant of variation. That constant of variation is determined by doing y over x, just like we did over here. We said every time we did y over x, we came up with the same number, and that number was 3. Well, let's apply that in this particular case. Let's do y divided by x for each ordered pair and see what happens. Well, 10 divided by 2 is 5. Negative 15 divided by negative 3, still 5. Let's keep going. 35 divided by 7 is 5. Negative 5 divided by negative 1, still 5. And 30 divided by 6. Every time we did y divided by x, we got the same result. And that same result is what we're calling k, the constant of variation. So the answer to the question, is this direct variation? Yes. What is k? We've already identified that. Well, now let's put it together. When we found k, it's really pretty easy to write the equation. We just replace the variable k with that actual constant. All right. In problems 18 to 22 even, you're told that you have a direct variation relationship, and you're given a y value and an x value. Well, it's really like saying this. They're telling you that this particular point, 7, 2, is on the line. Okay? So you don't have to do this, but maybe just giving a little picture will help put this in context. Remember, 0, 0 is always on the line for direct variation. The line always goes through the origin. And we also were told that the point 7, 2 is on the line. All right. So what we're after is, what is the equation for this line? Well, you can arrive at the k number pretty easily by doing y over x. We talked about that earlier. And in this case, if we do 2 over 7, y is 2, x is 7, that's our k. And let's just go one step further and write the equation for this direct variation, y equals k times x. Well, k is known now to be 2/7 times x. All right, so that makes answering letter B pretty easy. Let's find out what the output is, or in other words, let's find y when we do the input as -5. Well, let's see. Output given an input of -5. That means our y, which is what they're asking us to find, is -10 over 7. All right, so this little graph was extra. You don't have to do that, but I'm just hoping to show you that the slope in this case, if we're going back and using more familiar terminology, is up to right 7. And that's how we came up with k, y over x. All right, so let's try another one of those. This time we're given the ordered pair 2, -2, and we're asked to find k. Well, there's a couple of ways you can go about this. Remember, you always find k by doing y divided by x. And in this case, -2 over 2 is -1. And knowing k means that my equation looks like this. Y equals k, which is -1 times x. Well, let's find the value in this case of y if we let x be replaced with -5. And that's pretty easy. The opposite of -5, of course, is +5. Okay, let's move right along. If you'll notice, the directions have changed slightly. Before, we were asked to find y given a certain x, or find the output with this input. Well, now they've changed it around on us a little bit. Now we're finding x given a certain value for y. But the way we find k, that constant of variation, it's crucial in doing these direct variation problems. You need to find out what k is. It's always y divided by x. In this case, that's going to be 4 divided by -2, which is -2. And then let's let that lead us into the equation. The equation is y equals k times x, and we've found out that k is actually -2. And now we can answer this part. If we let y become 6, let's find x. So we solve for x by dividing by -2 on both sides, and we got our answer. X is -3. Okay, we're almost done. In the block of problems 33 to 39 odd, notice you're doing the odd ones this time. Once again, we're asked to write the equation for a direct variation function. And we're not actually supposed to do the graph. We're just told that this particular graph passes through the point -3, -7. So, in other words, if we know that this is a point, to go along with, of course, 0, 0, then what is the equation that represents this graph? Well, let's go back, and we've done this several times. Let's find k. K is y over x, which in this case is going to be -7 over -3, which simplifies negative divided by negative, of course, is positive. Well, the directions just tell me to write the equation for this particular direct variation relationship. Well, here it is in general. This is direct variation in general terms, and this is how I would answer this particular problem. Sorry. I'm just going to replace what I came up with, the constant, as 7/3. That replaces k. And I've got my equation. So that's really not too bad at all. Don't have to graph anything. Just use this ordered pair as your x and y to help you find the constant, and then that can lead you to the equation. Okay, well, you know what the assignment is. You can check RenWeb, and I hope this helps with the homework problems that you have to do. But if not, after you've watched this and you still have questions, send me an email, or you can always come in the morning, and I'll be glad to help you.